But hi everyone, I'm Frank. I work at the University of Edinburgh. Um, I'm going to um, speak about the work that I have been doing together with Daniel Hillerström about implementing the stack switching proposal in Wasmtime. So as a bit of context, there is a stack switching proposal. There is also a subgroup of the WASM CG working on this proposal. And the idea is to bring non-local control flow to WASM. And you just need to move this window really quick. And the idea is that this way we enable various control flow features in source languages, such as async await, coroutines, lightweight thread generators, first-class continuations, you name it. And the proposal itself kind of originated with something that's based on Plotkin and Predna's handlers for algebraic effects, which are kind of inherently asymmetric. You have kind of parent-child relationships between continuations. And then there was an Uppsala paper in 2023 about this, about kind of this earlier version of the proposal that we have now. And then later on, the proposal evolved, most notably by adding the switch instruction to it, which is kind of optimized for the use case where you actually want to do something that's more similar to symmetric switching. And I'll talk about the difference between these two things a little bit later. And finally, now, a couple of months ago, the proposal has now moved to stage 2 of the process. And we have two implementations. One of them is the reference interpreter, and the other one is in a fork of Wasmtime, which is an industrial strength standalone WASM engine. And we're currently being in the process of upstreaming this, hopefully having a PR open for that this week. So just as a kind of crash course in how the proposal looks like, here's the instruction set. So on the module level, we reuse the tags that were introduced by the exception handling proposal, but we add results types to them. And these tags are basically the delimiters or the effects based on the kind of perspective you have on stack switching. And we add heap types for first-class continuations. And then in terms of the most important instructions of the proposal, we have one to create a continuation from a function reference. And then the next two instructions are basically the ones for the kind of asymmetric switching. So we have one instruction called suspend, where you provide a tag which suspends the currently running continuation and goes back to one of its parents. Or from the kind of effect handler perspective, you're just performing an effect. And then we have an instruction for resuming a continuation, which basically means installing a new effect handler. So we use these tags to denote, oh, on this effect, use this block to handle this effect. And then finally, we have this switch instruction, which allows you to, rather than going to your parent, directly switching to a different continuation. And again, I'm going to speak about this instruction in a bit. So now, kind of as a very simple example, I'm not going to show any code, but just to give you an idea. So here's kind of the hello world of at least the asymmetric use case, which is like a generator. So we have two functions here, the consumer function and the generator function. And the idea is that the generator function runs in a continuation. So what the consumer will do is it will resume it initially. That's kind of the right arrow, which makes the consumer continuation, or maybe it's the main stack, the parent of this continuation running the generator. And then the generator can suspend itself and in the process provide a value back to the consumer. And this way they can kind of go back and forth. The consumer resumes the generator and the generator suspends itself to go back to the consumer. And here you also see this kind of asymmetric nature. The consumer, the parent, uses the resume instruction, and the other one uses the suspend instruction. And now, if you kind of remember the examples I've given on one of the earlier slides, we had all of these kind of use cases like lightweight threads, coroutines, and I'm going to provide an example here with just two functions, task 1 and task 2. And the idea is that they kind of executed some tasks, and we want to switch from task 1 to the other task because task 1 is blocked or something like that. And if we use kind of the techniques that I've described so far, the kind of asymmetric switching, then we would have a situation where you have some kind of stack running a scheduler, which is then the parent of the task one that's currently running. And then task one, if it wants to kind of hand execution over to some other task, it would just suspend itself. And then the scheduler would pick the next continuation to run, in this case, the one that's running task two, and resume that one. And that would work perfectly fine. The only issue is kind of that our goal was to switch from task one to task two. But we've now actually executed two task switch in the process. So the idea of this switch instruction is that we save one stack switch. So we still have parent-child relationships, and we still have these tags to kind of act as delimiters, but we now have the ability to directly go from task one to task two with just kind of one actual stack switch being executed on the machine. So that's kind of a high-level introduction to the proposal itself that I wanted to give. And what the rest of this talk is going to be about is mostly kind of the journey that we've taken to actually implement this in Wasmtime, because this was always kind of following this challenge that we had, which is implementing a relatively complex feature in an industrial strength WebAssembly engine with just limited resources. And the limited resource here being people, because in the beginning it was Luna, Phipps Costin, and Daniel working on this. And then later on, me and Daniel working on this. But basically, only ever two people at the same time, and not really these two people working full time on it either. And so that's kind of the main constraint here. And the process that kind of we ended up with was the following. And it's not so much that we kind of sat down and came up with this grand plan in some way, but it's kind of over time we figured out that the best way to actually do this and achieve this is these relatively high level steps that I'm then going to provide some details on later. So the idea is to kind of start with a relatively inefficient prototype that focuses on ease of implementation. And then kind of the next two steps, even though I've numbered them 2 and 3, they're kind of happening in parallel. So the idea is to kind of, on one hand, figure out the design where you eventually want to get to for higher performance, and then make incremental changes towards that implementation goal. In particular, no kind of big bang on one day you kind of rewrite your entire application or your entire implementation. But of course, the second step and the third step, they go hand in hand because you may not have figured out how exactly it will look like from day one. So the design will evolve over time. And then finally, in the end, you will hopefully arrive at an optimized implementation. And in our case, the starting point was this kind of relatively inefficient but easy to implement kind of baseline or prototype implementation. And the kind of architecture of Wasmtime in general is shown here on the right. So the pipeline looks basically like this. We start with your WASM program, and then we translate it to CLIF, which is the intermediate format used by CraneLift. And CraneLift is the compiler that's kind of shipped as part of Wasmtime. It's supposed to be relatively independent from Wasm itself, but it's the compiler used by Wasmtime in the end. And one important, hearing myself, a bit weird. There's a slight echo in the chat now. I guess I'll have to. Um, So of course the format has call instructions, but one particular way of doing calls is kind of using an infrastructure that's part of Wasmtime, which allows you to call into runtime functions shipped part of Wasmtime. So you're basically able to cross the boundary between Cliff, kind of CraneLift generated code, and Rust precompiled code running in Wasmtime itself. Sorry, can we somehow fix this echo that I'm having? Because right now I'm hearing myself in a very loud way, which is a bit irritating. Is it still there? Oh, I think it's gone. Ah, good. Thank you. I will go back to my talk. Here we go. So I was mentioning kind of libcalls, and in a sense they are an escape hatch because they allow you to execute arbitrary Rust code by calling into them from the CraneLift generated code. And we've used them very liberally in the kind of initial version of what we've written. Because most importantly, we've used them to perform the actual stack switching by calling into an existing library called Wasmtime Fiber. I'm going to talk about a bit more of that in a moment. So the actual stack switching happened this way. And then also to perform allocation. And it was the case a couple of times that we would simplify the implementation work this way. So basically, whenever something was difficult to do, rather than emitting the right Cliff code, we would just implement it in Rust first and then call into that. And now some details on Wasmtime Fiber, this library that we used. It's a general-purpose stack switching library that's developed as part of Wasmtime, mostly because there is already a feature for asynchronous computation in Wasmtime, but that's not kind of integrated into the core language. So that's basically from the embedder side. So that's not what our proposal is about, but it meant that this library was there for us to use. And based on the platform, what you have at the heart of this library is basically handwritten assembly, which does the things that you would expect from a function or from functionality that does stack switching. So basically, save your registers, adapt your stack pointer, and then jump somewhere else. And here on the right, we kind of see the high-level stack layout that this uses. So in my examples, stacks will grow down. So at the very top, and this stack here is suspended right now. So at the very, very top, we have the stack pointer where we left off, in a kind of reserved area at the very top. And then below that, we have the regular stack frames. Then we have caller save registers because we actually, the switching function is a function, so we called it like a function. And then we have the stuff that this handwritten assembly function itself saves, like the instruction pointer, frame pointer, and the call save registers. So that's what the Wasmtime Fiber library does. Now I want to talk about the architecture that we wanted to get to eventually. And the main goal here was that eventually we wanted to perform the actual stack switching itself from code that's generated by CraneLift rather than using libcalls for that. And in particular, we want to get rid of basically all the libcalls except the one for cont_new, because that needs to perform allocation, so it would probably always have to need to happen in the runtime. So the idea was that we would add a new Cliff instruction that would then compile to the right kind of basically what the old Wasmtime Fiber switch or something similar to what this was doing in the past. And the kind of the guidelines here for us was that this was supposed to be like the minimal addition to CraneLift that we needed to do this kind of thing, and for it to be platform independent. And now here in this little speech bubble, instead of a call that we compile now, the idea is to directly compile to this Cliff instruction, our WebAssembly. And now we see some details about this instruction. So the idea is that it acts, instead of kind of being given the data that it needs to act on, like the new instruction pointer and the new stack pointer, we're not giving that directly to the instruction, but in order to be platform independent, we give it basically pointers to memory where it will find that data, and also a pointer to where it's supposed to write the current state. And then we have the ability to pass around some payload. And we call these areas that it acts on control context, and the actual layout is platform dependent, but it will contain something like your stack pointer, your instruction pointer, stuff like that. And interestingly, it's actually providing symmetric switching. So even though the proposal as a whole is based on asymmetric switching, this core primitive that we needed to add to the compiler is actually doing symmetric switching. And here on the right, we see that the stack layout that this instruction uses is actually quite similar to what we saw with Wasmtime Fiber. So now at the top of the stack, this kind of reserved area, we have the control context, which contains a bit more now, not just the saved stack pointer anymore. But for example, it contains the pointer down to the end of the stack still. Then we have the regular stack frames of the stack that we're running in this continuation. And in the end, we have the saved registers. So basically all of the data registers down here, and up in the control context, we have like the kind of control registers in a sense. And if you compare these two, they are relatively similar, and that's not a coincidence. So we were quite interested in making this happen and kind of to ease the transition. But it turned out that actually with the constraints we had, this was a natural pick. So we didn't kind of push ourselves into a corner by choosing a layout that's kind of deliberately similar to the old layout that Wasmtime Fiber used, but it actually turned out that the similar layout was a good choice anyway. And actually, what I'm not showing here is that we had a third layout, which is kind of in between the two, that made the transition even easier. So that one day we could just flip a switch and go from Wasmtime Fiber, or rather our own forked version of Wasmtime Fiber, to the new stack switching instruction. And here are some benchmarking results. This is basically just testing the performance difference at the one commit where we kind of flip the switch. And these are all micro benchmarks, so take them with a big grain of salt. But still, if you look at this very last line here, that's basically a micro benchmark that just does suspend and resume instructions in a hot loop for like a billion iterations. And here we're seeing like a 6x performance improvement. And of course, that's great. We're happy with that. But that's actually like surprisingly good. Like the lib calls have some overhead, but we wouldn't necessarily expect that to be like a 6x factor. And I'm running out of time, which is why I have an analysis of why this is happening. There's actually something really interestingly on the CPU architecture level happening here, but the TLDR is that function returns and stack switching really don't like each other. They confuse the CPU's prediction unit for returns, which means that at every stack switch we had consistently had 4 mispredicts in a row. And that's actually where this big performance difference came from. If you're curious about the details, then talk to me. And now I want to kind of go back to these 4 steps that I mentioned earlier and kind of reiterate what that exactly meant for us. So I said the first step is kind of to start with this inefficient but easy to implement prototype, which in our case we built on existing mechanisms, which on one hand was this Wasmtime Fiber library and the libcall mechanism. And in particular, and this was kind of a shallow implementation. We didn't have the touched crane lift at all at this stage, which was very good because like none of the people who worked on this had ever touched Wasmtime or crane lift before. So kind of reducing the surface area that we needed to touch for the initial prototype was like a huge help. And then for every time something was very complicated, we just used libcalls in the initial version. And then to kind of sketch a design for the more optimized implementation in parallel to the other orthogonal implementation work, I worked on a prototype for how the stack switching and crane lift should actually look like. And then over time, we kind of adapted our own copy of Wasmtime Fiber to incrementally move in that direction until we eventually switched to the actual stack switch instruction. And of course, what I haven't really gone into today is all of the other small improvements that were not directly related to the stack switching itself, but things like payload passing and allocations and stuff like that. But of course, there were a lot of other things that had to happen along the way. And then fourth step ideally is you arrive at an optimized implementation. And as I said, we're currently kind of applying the finishing touches to OPR to actually upstream this. And here are some resources if you're curious. And other than that, I think it's question time.
Frank, hello. Are you able to hear us?
Yes, I am.
Great.
This is a nice change to the last 20 minutes.
Okay, we may have to do some toggling to make sure you're not hearing your own echo, but we'll just try and make that work. So, do we have any questions for Frank? One on the back.
Hello, I hope you can hear me.
I can, yes.
Yeah, so I was comments as a question, but I was actually surprised when you said almost like on stack switch because it confuses the return predictor. I was wondering if you have any more information on that, if something...
You're currently kind of like always like the audio is on and going on and off. It's really hard to hear you.
Okay, let me try again. Maybe I just didn't hold the mic close enough. Is this better?
Oh yes, now it's better.
Yeah.
Yes.
So I think you briefly mentioned you had multiple mispredicts for each stack switch, and I was kind of surprised because at least that's not my mental model of how the CPU works. I'm wondering if you have any more information on it, because I'm kind of curious what's happening under
Yes.
the hood. Yeah.
So this is not because of stack switching in general, but the reason is that we always had 4 nested calls, and the 4th nested call would do the actual stack switch, and then you would go to another stack where you would have to return from 4 different functions. And these 4 different functions were all So the problem was mostly we had these 4 nested functions on each stack, and we switched and then returned from 4 different functions, and this is what confused the return address prediction terribly, because the return address prediction expects whenever you return, right, the return address will be the address of the last call. It tries to match them together, but this isn't true anymore in the stack switching scenario, where you're basically popping stack frames on one stack, then you're going to another stack, and then you're popping frames, but they're not the frames you've just added. They are different frames, and that just confuses the CPU, if that makes sense.
Yeah, I think that did. Thank you so much.
So this is a very related question, but I'm curious if you have any hardware that supports modern shadow stack instructions, if you have any thoughts on performance with shadow stacks, which I imagine may improve your misprotect situation, but also will mean you need a kernel context switch in some cases on Intel, I think. So just curious if you have any thoughts on that topic.
To be honest, it's not something we have looked at at this stage. It's definitely like something we want to think about, but we haven't done so at this stage.
Great, I think that's a natural place for us to end the questions. Let's all thank Frank one last time.